Hello and welcome back. In this example, we're going to be given two lines. We'll have parametric equations for each of them, and we want to know if the two lines intersect. So we're going to look at two examples of this. We'll start with this one. So here I have two lines that are given in parametric form, x of s, y of s, z of s, and x of t, y of t, z of t. So the first thing I'm going to do here is get vector equations for these. That's one way to proceed with this. So I'm going to call this one R1 of t, and I'm going to call this one R2, and this uses the parameter s. So I'm going to use these two. So R1 of t, first off, looks like, so now going from parametric to vector equation, this will be 2 plus 3t in the x, just 3t in the y, and then 1 minus t in the z direction. My R2 of t gives me 4, R2 of s, sorry. 4 plus 2s minus 3 plus 3s, and then just negative 2s. And I want to know, are there any values of t and s for which R1 of t is equal to R2 of s? That's the question. So I'm going to set these two equal to each other. So I have 2 plus 3t, 3t, 1 minus t, equal to 4 plus 2s minus 3 plus 3s minus 2s. And what I can actually do is subtract these. These are two vectors. I can subtract them. If I subtract, say, this one from this one, I'll be left with the 0 vector over here. And so I'm going to do that. I'm going to subtract component-wise. So let's see, 2 minus 4, that's negative 2. And then I'll have a 3t minus 2s in the x component. Over here, 3t minus this, so that'll be a positive 3 plus 3t minus 3s. And over here, I have 1 minus t minus negative 2s, so that's going to look like 1 minus t plus 2s. And I'm operating on this thing. I subtracted this vector over here, so I'm left with the 0 vector, 0, 0, 0. And so that gives me a set of 3 equations. I have now, let's see, I need, in order for there to be parameters t and s that give this to the 0 vector, I need each one of these to be equal to 0. Remember that two position vectors are equal if and only if their components are equal. And so that tells me 3 equations now. I have negative 2 plus 3t minus 2s needs to be equal to 0. I have 3 plus 3t minus 3s has to be equal to 0. And I have 1 minus t plus 2s has to be equal to 0 as well. So now I need to ask the question, is there a solution to this system of equations? So if you're fancy with matrices, you can work this out. With matrices, if you're comfortable with your linear algebra, I'm just going to do this, I think, by a substitution method. Let's just do substitution. So I'm going to take this first equation. So this first equation, I'm going to find t in terms of s. So if let's see, if I add the 2 to the other side, add the 2s, and then divide by 3, I'll get t equal to, what did I say, 2 plus 2s all over 3. So that tells me what my t would have to be equal to in terms of s. And now I can take this and plug it into one of these other two. So which one? Who knows? I'm going to try this one. So now take this and plug it into this equation. And what'll that yield? I'm actually going to move this down here now. Plugging that in, I have 3 plus 3 times 2 plus 2s over 3 minus 3s. And what's that equal to? So this is 3 plus, so this is actually why I chose the second equation, because I knew the 3's were going to cancel out here. I wouldn't have to mess with fractions. 2 plus 2s minus 3s. And I know that this needs to equal 0. So let's keep going with this. I'm running a little bit out of room. Let's see, 2s minus 3s. That gives me a negative s over here. I'll move that to the other side, and I get s equals 3 plus 2 equal to 5. So that tells me s is equal to 5 if I then take that and substitute it up here. So that's 2 plus 2 times s is 5. So that's 2 plus 10, that's 12 divided by 3. That gives me 4. So what this is telling me is that if these two lines intersect, then s must be equal to 5 and t must be equal to 4. So let's now check this against our third equation and make sure that this is a consistent system of equations. Let's see. If I plug, so now check with the third equation, pull that down here. So I'll do 1 minus my t, which is equal to 4. 1 minus 4 plus 2 times 5. 1 minus 4, that's negative 3, plus 10, I get 7, which is not equal to 0. So that is, if these two equations, if these two lines intersect, t must be equal to 4, s must be equal to 5. However, if t is equal to 4 and s is equal to 5, then the z components of my two lines do not match up. And therefore, there are no points of intersection. So what this tells me, since I've reached a contradiction, right, this is not equal to 0 like it should be, so that's a contradiction. What this tells me is that there are no intersection points. So these lines do not intersect. So that's the idea, is you get a system of linear equations, and then whether or not you solve that tells you whether or not there's an intersection point, or what that intersection point looks like. It's possible we actually have the same line twice and we get an infinite number of intersection points. That's also a possibility, right? We have a system of 3 equations with 2 unknowns. That tells us there's 3 possibilities. No intersection points, 1 intersection point, or infinitely many intersection points. All right, let's look at another example here. Determine whether L1 and L2 intersect. If they do, find the point of intersection. So you might notice in that last one, what I was really doing here, these equations, I was taking the x component of L1 and subtracting the x component of L2. That gave me my first equation equal to 0, right? 2 minus 4 is negative 2, 3t minus 2s. So really, why don't I just jump to that? So if these things intersect, then it must be the case that 3 plus t minus 2s must be equal to 0. We also need to have that 4 minus t minus negative 1 plus 2s has to be equal to 0. Subtract those. And then the z's, 5 plus 3t minus 4s also has to be equal to 0. So here's my system of 3 equations, my linear system. And now I can start solving this. Maybe here I want to do a little bit of algebra. So this is the same as, let's see, 4 minus negative 1. So that's 5 minus t minus 2s. Okay, the rest are simplified enough. So how about, this one looks easy enough to solve. I'll add t to the other side. I'll get t equal 5 minus 2s. I'll take this and substitute it in, I don't know, how about to this first one? Let's sub it in for t here. Then that gives us 3 plus t is 5 minus 2s. Minus 2s. Subtract another 2s equal to 0. Simplify that. That's 8 minus 4s equal to 0. That tells me that 4s is equal to 8, which tells me s must be equal to 2. I can then take that, substituted in here where my relationship between s and t is given. So s equal to 2, this would be a minus 4, t would be equal to 1. So if these lines intersect, s is equal to 2, t is equal to 1, let's check if the z components, or the z coordinates of my lines match up with s equal to 2 and t equal to 1. So I'll say here s equal to t equal 1. Let's see what we get. 5 plus 3t, and t is 1, minus 4 times 2, so that's 8. 3 minus 8 is negative 5. 5 plus negative 5 is equal to 0, which it should be. So when s is equal to 2 and t is equal to 1, we have that the lines intersect. So let's say L1 and L2 intersect when, if we think of t and s as like two different time parameters, I can say when s equals 2 and t equals 1. Now, I don't just want the parameters that give me the point of intersection. I want to actually find the point of intersection. So in order to do that, I just plug in 2 and 1 in the vector equation. So L1 here, if I plug in x, or if I plug in t equal 1, so the point where they intersect, I'm going to call this R1. And I'll call that, I don't want to say equal to, I'm going to call this equation R1 of t, and this equation is going to generate R2 of t, R2 of s. And then what I want to work out is what's R1 of my t value, R1 of 1. So that'll be my x value, my x component will be 3 plus 1 will be 4. My y component will be 4 minus 1, that's 3. My z component will be 5 plus 3, that's 8. And so this should be my point of intersection. I'm going to check that this actually is a point of intersection. That is, I'm going to evaluate R2 of 2, and that should give me 4, 3, 8 as well. So when t is equal to 1, R1 gives me this point. When s is equal to 2, R2 gives me another point. They should be the same because this is what I'm claiming, they intersect. So R2 of 2, so that's going to be 4, right? 2 times 2. And then I have negative 1 plus 2 times 2, so that's 3. And finally, s is equal to 2, s component is 8. So yes, they intersect, and the point is, so intersect at the point 4, 3, 8. A little subtlety here. Here I had vector equations. These were spitting out vectors that pointed to the point on the line where they intersected. This, with parentheses, is the actual point. So this is what I want, not a vector. I want the point that's on the line, that's on both of the lines. So these two intersect at a single point. It is possible that we end up with a free variable when solving this set of linear equations, in which case we will get a line out as the intersection. That's an infinite number of points. And in that case, the two lines are exactly the same. So in this case, they intersect at just one point, and so we've gone over two of the possibilities here. All right, that's it for this video. I will see you next time. We'll start, well, not quite, not next video, but in a few we're going to talk about planes. I'll see you there.